topic is alkyl halides from the book Modern Chemistry. Introductions. The compound obtained by the replacement of one or more hydrogen atoms of a hydrocarbon of a corresponding number of halogen atoms are known as halogen derivatives. These derivatives are subdivided as mono, di, tri, tetra halogen derivatives according to the number of halogen atoms present in the molecules. In addition, the halogen derivatives may be further classified into different classes depending upon the nature of parent hydrocarbons. There are two main classes which may be further subdivided as given below. Aliphatic halogen derivatives. These are halogen derivatives of aliphatic hydrocarbons in which one or more hydrogen atoms of the hydrocarbons have been replaced by an equal number of halogen atoms. Depending upon the nature of the aliphatic hydrocarbons, they are further divided into three types. Haloalkanes. The halogen derivatives such as CH3Cl, CH2Cl2 and CHCl3 obtained by the replacement of one or more hydrogen atoms of alkanes are known as halogen derivatives of alkanes. These compounds are very reactive and undergo numerous reactions which are used in the preparation of a large number of aliphatic compounds. Monohalogen derivatives of alkanes are commonly known as alkyl halides as discussed below. Haloalkenes. These are halogen derivatives of alkenes. Monohalogen derivatives of alkenes are known as alkenyl halides. For example, vinyl chloride, allyl chloride. Haloalkynes. These are halogen derivatives of alkynes. Monohalogen derivatives of alkynes are called alkynyl halides. Halogen derivatives of aromatic hydrocarbons. These are halogen derivatives obtained by the replacement of one or more hydrogen atoms of aromatic hydrocarbons by halogen atoms. These may be subdivided as nuclear substituted derivatives. These are halogen derivatives of aromatic hydrocarbons in which the halogen atom is directly attached to the benzene nucleus. For example, chlorobenzene, orthobromotoluene. Side chain substituted derivatives. These are halogen derivatives of aromatic hydrocarbons in which the halogen is linked to the carbon of the side chain. For example, benzyl chloride, benzyl dichloride. The side chain derivatives are very reactive compounds which are similar to halogen derivatives of alkanes. On the other hand, nuclear derivatives are much less reactive and undergo only a few substitution reactions under strong conditions. In this chapter, we shall discuss the chemistry of alkyl halides. Alkyl halides. Alkyl halides or monohalogen derivatives of alkanes are the compounds obtained by the replacement of one hydrogen atom of an alkane by a halogen atom. They have the general formula CnH2n plus 1 X or Rx, where X represents a halogen atom and CnH2n plus 1 or R stands for an alkyl group. For example, methyl chloride, ethyl bromide, and isopropyl iodide. In a wider sense, however, alkyl halides include even side chain monohalogen derivatives of alkyne benzenes and cycloalkanes. For example, benzyl chloride, cyclohexyl chloride. It must be noted, however, that the compounds containing a halogen directly attached to a benzene ring are in no case covered by the term alkyl halides. Such compounds called aryl halides differ widely from alkyl halides in their method of preparation and properties and are treated separately. Classifications of alkyl halides. Alkyl halides may be further subdivided as primary, secondary, and tertiary halides according to as the halogen is attached to primary, secondary, and tertiary carbon atoms. Primary halides: N-propyl iodide, isobutyl bromide. Secondary halides: isopropyl chloride and secondary butyl bromide. Tertiary halides: tertiary butyl bromides and tertiary pentyl iodide. Alkyl halides are amongst the most reactive organic compound as the alkyl halogens can easily replaced by a nucleophilic reagent. Substituted alkyl halide exhibits the properties of other substituent groups also. For example, benzyl chloride displays the reactions of aromatic nucleus also in addition to the characteristic reactions of alkyl halides. It may be noted that the fluoro derivatives of alkanes, also known as fluorocarbons, differs from other halogens initiatives in many respects. For these reasons, alkyl fluorides and other fluorocarbons are treated separately from chloro, bromo, and iodo derivatives. As such, as we shall confine our discuss to alkyl chlorides, bromides, and iodides only, which are quite similar to each other. Nomenclature. Common system. In this system, individuals alkyl halides are named as halides of the particular group present in the molecule. For example, CH3Cl is named methyl chloride, while CH3CH2I named ethyl iodide, and so on. IUPAC system. According to this system, these compounds are named as given below. The longest straight chain of carbon atoms, including the carbon which carries the halogen, is selected, and the alkane corresponding to this chain is taken as the parent alkanes. The straight chain is numbered from the end, which gives the smallest number to the carbon carrying the halogen. The names of the halogen chloro, bromo, iodo, and the side chains along with their points of attachments are added before the name of the parent alkanes. For examples, we have 2-chloro, 3,4 dimethyl pentane. The common IUPAC name of a few members given below. CH3Cl. Common name methyl chloride. IUPAC name chloromethane. CH3CH2Br. Common name ethyl bromide. IUPAC name bromoethane. Structural isomerism in alkyl halides. Higher members of alkyl halides show two types of structural isomerism as given below. Chain isomerism. Alkyl halides containing 4 or more carbon atoms can exhibit chain isomerism. For example, the two chain isomerism of C4H9Cl are as follows: 1 chlorobutane and 1 chloro 2 methyl propane. Position isomerism. Alkyl halides having 3 or more carbon atoms can exist as position isomers. For example, C3H7I can exist in the form of two position isomers, 1 iodopropane and 2 iodopropane. In general, the total number of structural isomers of an alkyl halide is 2 n minus 2, where n is the number of carbon atoms. Thus, there are 4 isomers having the molecular formula C4H9Cl and 8 isomers having the molecular formula C5H11Br. Methods of preparations. The important method of preparation of haloalkanes are discussed below. From alcohols. Alcohols are generally prepared by the replacement of hydroxy group of an alcohol by halogen atoms. This can be done by using different halogenating reagents as given below. Action of hydrogen halides. Alcohols are converted into alkoalkanes by reaction with hydrogen halides under suitable conditions. For examples, ROH plus HX gives RX plus H2O. Primary and secondary alkyl chlorides are obtained by passing HCl gas into corresponding alcohol in the presence of anhydrous zinc chloride. For example, ethanols with HCl gives chloroethane and water. 2-propanol with HCl in presence of anhydrous zinc chloride gives 2-chloropropane plus water. Tertiary chlorides can, however, be obtained by the reaction between the tertiary alcohol and concentrated HCl even in the absence of anhydrous zinc chloride. For example, 2-methyl 2-propanols with concentrated HCl gives 2-chloro 2-methyl propane in presence of with water. Alkyl bromides and iodides can also be obtained by heating the alcohol with the excess of constant boiling HBr 48% or HI 57%. For examples, 1 propanol with HBr gives 1 bromopropane plus water. But in actual practice, hydrogen bromide and iodide are usually prepared in situ, that is during the reactions by using sodium bromide and concentrated sulfuric acid or potassium iodide and phosphoric acid. For example, CH3CH2OH plus NaBr plus H2SO4 gives bromoethane plus H2O plus NHS4. CH3OH plus Ki plus H3PO4 gives iodomethane plus water plus KH2PO4. In the above reactions, the order of reactivity of halogen acids towards alcohol is HI ज़्यादा HBr and then HCl. This is because this reactions involves nucleophilic attack of halide ions and alcohol Since the order of nucleophilicity of halides ions is iodine, bromine, chlorine, anions, the reactivity of hydrogen halides follow corresponding order, that is Hi, HBr, HCl. The order of reactivity of alcohol towards halogen acids is tertiary, secondary, primary. Majority of these reactions involves the formation of carbocation intermediate, as the order of stability of carbocations is tertiary, secondary, primary. The reactivity of alcohol follows the corresponding order tertiary, secondary, primary. Alcohol, the reaction of HCl with primary and secondary alcohols requires the use of a catalyst such as anhydrous chloride, because both HCl and primary and secondary alcohols have low reactivity. Anhydrous chlorides help in the cleavage of carbon-oxygen bond of alcohol. Action of phosphorus halides. Action of phosphorus halides on alcohols convert them readily into alkyl halides. For example, 3ROH plus PX3 gives 3RX plus phosphorus acid. The alkyl chlorides are produced by reactions between alcohols and PCl3 or PCl5. For examples, 1 propanol with PCl5 gives 1 chloropropane plus POCl3 plus hydrochloric acid. In case of the preparation of alkyl bromides and iodides, PBr3 and Pi3 required for the reactions are not very stable compounds. These are generally produced in situ by the action of red phosphorus or bromine or iodine. For examples, 1 propanol plus Pi3 gives 1 iodopropane plus H3PO3. Actions of thionyl chloride. Alkyl chlorides are conveniently obtained by reactions between thionyl chloride and alcohols in the presence of pyridine. For example, ethanol plus thionyl chloride gives chloroethane SO2 gas plus HCl gas. Addition of hydrogen halides to alkenes. Addition of hydrogen halides to alkenes yields alkyl halides. For example, ethene plus Hi gives iodoethane. Propane plus HCl gives 2-chloropropane. It may be recalled that in case of unsymmetry alkenes, the above addition reactions take place according to the Markovnikov rules. The rule states that when additions across an unsymmetric double bond take place, the positive part of the addendum molecule to be added goes to the carbon atom with the greater number of hydrogen atoms. It should be remembered that, however, the Markovnikov rule is not applicable in the presence of organic peroxides. The addition of HBr but not HCl or Hi to alkynes does not follow the said rules. The anti-Markovnikov addition of alcohol is known as peroxide effect or Karsh effect. For example, propene in absence of peroxides give 2 bromopropane, and in presence of peroxides gives 1 bromopropane. Halogenations of alkanes. Direct halogenation of alkanes under the influence of light results in the formation of alkyl halides. For example, methane plus chlorine gas gives chloromethyl and HCl. In actual practice, this method results in the formation of mixture of mono, di, tri, and tetrahalogenated compounds. At the same time, even monohalogenation of higher alkynes gives a mixture of isomeric monosubstituted products. For example, propanes in presence of Cl2 HV gives N-propyl chloride and isopropyl chloride. Therefore, this method is used only in industrials where complete separation of the mixtures obtained may not be necessary. Iodo and fluoro derivative are seldom prepared by this method. This is because iodination is reversible in nature, while fluorination takes place exclusively by halide exchange. Alkyl alloys can be conveniently prepared by heating the corresponding alkyl bromide or chloride with a solution of sodium iodide in acetone. For example, bromoethane in presence of NaI gives in presence of NaI and acetones gives iodoethane and sodium bromide. As compared to sodium iodide, sodium bromide or chloride is less soluble in acetone and gets separated during the course of the reaction. As a result, the reaction equilibrium shifts in the forward reaction. From silver salt of carboxylic acids, alkyl chlorides and bromines can be prepared by the action of fluorine or bromines on the silver salts of certain carboxylic acid dissolves in carbon tetrachloride, borodine, Hunts-Dicker reactions RCOOAg plus Br2 in presence of CCl4 gives RBr plus CO2 plus AgBr. Silver propanoate in presence of bromine CCl4 give bromoethane, carbon dioxide and silver bromide, while alkyl bromides can be obtained in fairly good yields. By these methods, the yield of alkyl fluorides are poor with iodine silver gives esters instead of alkyl halides. Physical properties. The lowest alkyl halides such as methyl chloride, methyl bromide, and methyl chloride are colorless gases. Methyl iodide and majority of higher members are colorless, pleasant smelling liquids. Members with very higher molecular weights are solid. Alkyl iodides turns brown on standing due to their decompositions by light. Boiling point. In general, alkyl halides have considerably higher boiling points than the corresponding hydrocarbon. This is due to the fact that alkyl halides have higher molecular masses than corresponding alkanes and are polar in nature. Therefore, they have stronger intermolecular forces of attraction than the corresponding alkanes. Amongst the alkyl halides themselves, the following points may be noted. For a given alkyl group, the boiling point of haloalkanes follows the order Ri, Rbr, RCls. This is because the magnitude intermolecular forces decreases with the decrease in the size of halogen atom. For a given halogens, the boiling point of alkyl halides increases with increase in the size of alkyl groups. This can be attributed to the increase in molecular size which leads to greater intermolecular interactions. For isomeric alkyl halides, the boiling point increases with branches. This is because branching of the chain decreases the surfaces and consequently the intermolecular forces of attractions become wider. Solubility. Even though they are polar in nature, alkyl halides are insoluble in water. This is because alkyl halides can neither form hydrogen bonds with water nor break the hydrogen bond already existing between water molecules. They have lower soluble they are, however, soluble in the organic solvents. Density. Alkyl chlorides are lighter than water, whereas bromides and iodides are heavier, the densities being in the order Ri, Rbr, RCs. With increasing size of the alkyl groups, the densities goes on decreasing. Chemical properties. Alkyl halides are one of the most reactive classes of the organic compounds. They undergo a variety of synthetically important reactions involving nuclear substitutions, eliminations, reductions, and formation of Grignard reagents. Naturally, therefore, they are regarded as one of the most important synthetic reagents in organic compound chemistry. The important reactions of alkyl halides are discussed below. Nucleophilic substitutions reactions. Alkyl halides contain sigma bond between sp3 hybridized carbon and the halogen atoms. The halogen atom is more electronegative than the carbon atom attached to it. Therefore, the carbon halogen bond is partially polarized, the carbon acquiring small positive charge and the halogen getting some negative charge. The positively polarized carbon can be easily attacked by nucleophilic reagents. When an alkyl halide is treated with a strong nucleophilic reagents, the halogen is readily replaced as a halide ions, which is a weak nucleophile as shown below. Thus, alkyl halides undergo a number of reactions called nucleophilic substitution reactions, in which the halogen is displaced as aldehyde ion by stronger nucleophilic reagents, giving a larger variety of products. The nucleophilic reagents may be negatively charged ions such as OH negative, Cn negative, and OR, generally added in the form of its sodium or potassium salt, or a neutral molecules having an atom with a lone pair of electrons such as NH3 or NH2. The halogen atom, which departs along with the bonding pair of electron, is known as leaving group. It it may be seen that in the nucleophilic substitution reactions, the carbon halogen bond undergoes heterolytic cleavage and the lone pair of electrons of the nucleus is used to form a new bond with carbon atom. Order of reactivity with respect to halogens. The strength of carbon halogen bond in different alkyl halides and therefore the reactivity of alkyl halides depends upon the nature of halogen atom. It is found that the carbon halogen bond strength follows the order CF, CCl, BR, CI The CF bond has the smallest bond length due to the small size of fluorine, therefore it has maximum strength. As the bond length goes on increasing with the increase in the size of the halogen atom, bond strength goes on decreasing. Since carbon ion bond is the least strong, it is broken more easily, so that the alkyl iodides are most reactive and the reactivity decreases in the. In other words, it can be said that the iodide only parts from the alkyl halides more readily and is the best leaving group. The order of ease of eliminations of the leaving group is iodide ions, bromide ions, chloride ion, and fluoride ions. Order of reactivity with respect to different alkyl groups. For different alkyl halides containing the same halogen, the order of reactivity is slightly dependent by the exact mechanism of the reactions as discussed subsequently. Replacement of halogens by hydroxyl group. Formation of alcohols. When treated with aqueous solution of potassium hydroxide or sodium hydroxide or the moist silver oxides H2O, which furnish OH negative ion, alkyl halides react with OH negative ions to form alcohol. For example, ethyl bromide with aqueous QH gives ethyl alcohol and potassium iodide. Replacement of halogens by alkoxy group. On treatment with the sodium alkoxide, alkyl halides react with alkoxide ions to form ethers. The reaction is called Williamson synthesis and is useful method for preparing ethers. Rx plus OR dash gives ether and X negative. For example, ethyl bromide with sodium methoxide gives diethyl ether and sodium bromide. Alkyl halides also react with dry silver oxide to form ethers. For example, C2H5Br plus Ag2O gives C2H5O, C2H52AgBr. Replacement of halogen by cyano group. Formation of cyanides and nitriles when treated with alcoholic solution of potassium cyanide. Alkyl halides react with cyanide ion to furnish mainly cyanides and nitriles along with a small amount of isocyanides. For example, methyl iodide with KCN gives methyl cyanide and Ki. Hydrolysis of cyanides themselves yields amides or carboxylic acids depending upon reactions conditions. For example, methyl cyanides and water with alkaline H2O2 gives acetamide on partial hydrolysis, and methyl cyanides on with H2O in presence of dilute mineral acid or alkali gives acetic acid plus ammonia on complete hydrolysis. Reductions of cyanides produces primary amines. For example, CH3CN plus 4 hydrogen atoms presence of Na and alcohol gives ethyl amines. The reaction is known as Mendes reductions. Reactions of alkyl halides with potassium cyanide is very useful for increasing the length of carbon chain and thus preparing higher member of a class of compound from its lower member. Replacement of halogen by isocyanide group. Formation of isocyanides or isonitriles. Alkyl halides react with silver cyanide at higher temperatures to give isocyanides along with small quantities of cyanides. For example, CH3I plus AgCN gives methyl isocyanide and AgX. Replacement of halogen by carboxylate group. Formation of esters. When heated with silver salt of carboxylic acids, alkyl halides react with carboxylic ions to yield esters. For example, ethyl iodide with silver acetate gives ethyl acetate and silver iodide. Replacement of halogen by nitro groups gives formation of nitroalkanes on heating with silver nitride. Alkyl halides gives mainly nitroalkanes along with a small amount of alkyl nitride. For example, ethyl iodide with the silver nitride gives nitroethane and sodium iodide. Replacement of halogen by nitride group. Formation of nitrides on reactions of alkyl halides with sodium or potassium nitride. However, the main product is alkyl nitride. Methyl iodide gives with the potassium nitride gives methyl nitride or sodium iodide. Replacement of halogen by amino group. Formations of amines on being heated with the alcoholic solution of ammonium alcohol halides was changed into primary amine as the amine formation is nucleophilic itself. It reacts further with alkyl halides to will ultimately a mixture of primary, secondary, and tertiary amines and quaternary ammonium salts. These reactions is known as Hofmann ammonolysis reactions. Ethyl alkyl with alcoholic ammonia gives ethyl amine and hydrogen iodide. In actual practice, the alkyl halide is initially attacked by nucleophilic ammonia to form a primary amine cell. This salt further undergoes an equilibrium reactions with ammonia to give primary amines. The free primary amines react further with alkyl halide as already explained. Replacement of halogen by hydrosulfide group. Formation of thioalkyls when treated with potassium hydrosulfide. Alkyl halides reacted with hydrosulfide ions SH negative to form thioalcohols. For example, ethyl iodide with potassium hydrosulfide gives ethyl thioalcohol and Ki. Replacement of hydrogens by mersaptide group. Formation of thioethers when treated with sodium mersapide. Alkyl halides react with mersaptide ions Rs negative and are converted into thioethers. For example, ethyl bromide gives with sodium ethyl mersaptide gives diethyl thioether and sodium bromide. Replacement of halogen by alkyl groups. Formation of alkanes Wurtz reactions. One reaction with sodium in dry ether saturated alkyl halides change into alkanes. It is believed that sodium initially reacts with a molecule of alkyl halides to form an alkyl carbanions. This being nucleophilic in character reacts further with another molecules of alkyl halide to yield an alkane. For example, methyl bromide with 2Na in presence of dry ether gives ethane and sodium bromide. Replacement of halogen by alkynyl group. Formation of alkynes. When treated with sodium salts of alkynes, alkyl halides react with alkynyl ions to produce higher alkynes. For example, ethyl bromide with sodium acetylide gives 1-butyne and sodium bromide. Replacement by groups derived from malonic esters or acetoacetic ester. Formation of substituted malonic esters and acetoacetic esters on reactions with carbon ions derived from malonic esters or acetoacetic esters added in the form of their sodium salts. Alkyl halides give rise to substituted malonic esters or substituted acetoacetic esters. Rx plus carbon anion derivative from acetoacetic ester gives alkyl derivative of acetoacetic esters and X negative. Replacement of halogen by aryl groups. Formation of alkyl benzines. Friedel-Crafts reactions or treatment with benzene and it is homologous alkyl halides furnish alkyl benzenes. For example, methyl chloride with benzenes gives in presence of anhydrous Cl3 gives toluene. Others reactions. Elimination reaction. Dehydrohalogenation when heated with a base such as alcoholic solution of potassium hydroxide or soda amine and alkyl halides undergoes elimination reactions by the loss of the halide ion together with the hydrogens ion from an adjacent carbon alpha beta hydrogens. Thus, alkyl halides get dehydrogenated on reactions with alcoholic potash or soda amine to form alkenes. For example, and propyl bromide with alcoholic KOH gives propylene plus KBr plus H2O. Sometimes an alkyl halide can undergo eliminations in two different ways, forming a mixture of products. The preferred product in such a reaction is the alkene, which is more highly branched at the doubly bound carbon atom. This generalization is known as Sertzeff rule. Two bromobutanes in presence of alcoholic QH gives 2 butene 80% and 1 butene 20%. Reductions of alkyl halides on treatment with nascent hydrogens produced from an acids or ordinary halogens in the presence of catalyst. Alkyl halides get reduced into hydrocarbons. For example, ethyl bromide with two molecules with the two hydrogen atoms in presence of zinc and HCl gives ethane with HBr. Reactions with active metals. Alkyl halides react with active metals like lithium, sodium, magnesium to form different products. Reactions with magnesium. Formation of Grignard. Isomerizations on heating to about 573 Kelvin or even lower temperatures in the presence of Lewis acids such as anhydrous ElCl3 alkyl halides undergo isomerizations to form products in which the position of halogen is changed but carbon skeleton remains the same. For example, n-butyl bromides in presence of dry ether gives secondary butyl bromide. Types of nucleophilic aliphatic substitutions, first order and second order reactions. We have learned above that alkyl halides undergoes a variety of nucleophilic substitution reactions. It is interesting to note, however, that all nucleophilic substitution reactions does not take place by the same mechanisms. On the other hand, there are two different mechanisms possible for nucleophilic aliphatic substitution. First is biomolecular nucleophilic substitutions, abbreviated as SN2. Unimolecular nucleophilic substitution, abbreviated as SN1. Let us illustrate the mechanism by considering hydrolysis of an alkyl halide by hydroxyl ions. Biomolecular nucleophilic substitutions, SN2. According to the mechanism, the reaction is believed to take place by a concentrated process involving a single step attack of hydroxyl ions or any other nucleophilic reagents take place simultaneously with the loss of halide ion, that is the bond between carbon and hydroxyl ions is being formed at the same time the carbon halogen bond is being broken. This means that the rate of reaction should depend on the concentration of both the reagents. As such, the rate of reactions may be expressed as R is equal to K RxOH negative. Since the rate of formation of alcohol is found to be proportional to the concentration of both alkyl halides and hydroxyl ion, the reaction is said to follow the second order kinetics. A single step nucleophilic substitution reaction of this type, which proceed by simultaneously collisions of two particles, is known as biomolecular nucleophilic substitution. A simple and prominent examples of SN2 substitution is provided by the hydrolysis of methyl bromide by hydroxyl ions in aqueous solution. The reactions may be depicted as nucleophile plus substrate, that is tetrahedral, gives transition state, and then product tetrahedral, which is tetrahedral and bromide negative ion. It may be noted that the hydroxyl ion attacks the carbon on the side opposite to the bromine because the attacking nucleophile cannot approach the methyl bromide molecule from another side due to repulsions by the negatively polarized bromine. This is refers to the backside attack and is supported by stereochemical evidence. As the hydroxyl ions approaches the carbon atom from the backside, a transition state is reached in which there is a partial formulation of carbon and OH bond, and at the same time a partial breaking of carbon and bromine bond. The central atom in the transition state acquires sp2 hybridization as the electrons on hydroxyl ion begin to be shared by carbon. The negatively charged on the hydroxyl ion decreases. Similarly, bromine develops a partial negative charge as this partially removes the pair of electrons shared with carbon. The transition state is quickly transformed into the final product, that is the methyl alcohol and bromide ion. Since the formation of transition state involves collisions between two particles, the reaction is obviously biomolecular. This is confirmed by the fact that the rate of the reaction depends upon the concentration of both the hydroxyl ion and methyl bromide in accordance with the rate equation. The energy profile diagram of the reaction is given below. One side there is energy and the second side is progress of reaction. Stereochemistry of SN2 reactions. The postulation of backside attack by the nucleophilic reagent in SN2 reactions requires that the configuration of the product should be opposite to that of the reactant. This has been found to be so in actual practice that can be clearly shown by considering the alkaline hydrolysis of optically active 2-bromooctane CH3CHBr C6H13. It should be worthwhile to note before proceeding further that 2-bromo-octane has the same configuration as 2-octanol as shown below. 2-bromo-octanes and 2-octanol. Now the hydrolysis of 2-bromo-octane with aqueous sodium hydroxide solution follows SN2 mechanism and result in the formation of plus 2-octanol. In view of the similar configuration of minus 2-bromo-octane and minus 2-octanol, the configuration plus 2-octanol must be opposite to that of minus 2-bromo-octane, as such that the reactions may be represented as. It is apparent that the OH group occupies a position occupied opposite to that previously occupied by Br, or in other words, the configuration of alcohol is opposite to that of the bromide. Such a reaction in which the configuration of a product is opposite to that of the reaction is said to place with the inversion of configuration. All SN2 reactions proceed with complete inversion of configuration. Note, it is not necessary that inversion of configuration in a reaction must be accompanied by a change in the direction of rotation of the new compound form, and vice versa. This may happen in some cases, as in the example cited above, and may not happen in other cases. Factors affecting influencing the occurrence and rate of SN2 reactions. The occurrence of SN2 reactions and their relative rates in different cases depends upon the following factors: nature of alkyl groups in alkyl halide, steric factors. In order to compare the relative reactivities of alkyl halides having the same halogens in SN2 reactions, let us first study the effect of the site of the groups attached to the carbon carrying the halogen atoms. To understand that, it may be noted that in case of the hydrolysis of methyl bromide, the reactant methyl bromide and the product methyl alcohols contain tetrahedral carbon, but in the transition state the carbon atom is bonded to 5 atoms. When the hydrogen atom in methyl bromide are successively replaced by larger groups such as CH3 and C2H5, there is an increased crowding around the central atom. This gives rise to a particularly strong non-bonding interactions in the transition state because of the presence of 5 groups attached to the same carbon. As a result, the energy content of the transition state rises and does the E activation for its formation. Naturally, therefore, the rate of the reaction slows down. It is clear from the above discussion that the relative reactivities of alkyl halides in the SN2 reactions are mainly related to steric factors, that is, factors pertaining to the sizes of the groups. In keeping with the observations, the order of relative reactivities in such reaction is found to be methyl halides, primary halides, secondary halides, and tertiary halides. Nature of halogens atom in alkyl halides, elimination of leaving groups. In SN2 reactions of alkyl halides, the halogen atoms ultimately leaves the transition states in the form of a negative halides ion to form the final product. The more easily the X negative ion is eliminated, the more the rate of the reaction. The ease with which the X negative is eliminated depending upon its basicity, the weaker the base, the better should as a leaving group. Now the order of increasing basic strength of halide ions is iodide ions, bromide ions, chloride ion, fluoride ion. Therefore, the order of ease of elimination of reactive would be iodide ions, ज़्यादा, bromine negative ions, then fluorine negative ions, then fluorine negative ions. Hence, the order of reactivity of alkyl halides having different halogens is I, ज़्यादा, RBr, RCl, and then Rf. Nature of nucleophilic reagents. Since the transition state in NSN2 reaction is formed by the attack of the nucleophilic reagents on alkyl halides, stronger the nucleophilic reagents, more rapid should be SN2 reactions. The decreasing order of the strength of a few common nucleophilic reagents is cyanide ions, ज़्यादा, RO negative, then OH negative, then CH3COO negative, then water. Nature of solvent. In SN2 reactions, the transition state is less polar than the reactions because in the transition state, the negative charge is dispersed over different atoms. Therefore, ions of polar solvents help solvate to the reactions more strongly than the transition state. As such, the polarity of the solvent slows down the rate SN2 reactions to more extent. Unimolecular nucleophilic substitutions reaction. where S denotes substitution and stands for nucleophilic and first for unimolecular. According to the mechanism, the reaction is considered as taking place in two steps. The first step is the slow and reversible and one involving dissociation of alkyl halides to alkyl carbocation and halide ions. The second step is fast one, which involves reactions between alkyl carbocation and hydroxyl ion to yield alcohols. The mechanism requires that the rate of reaction should be determined solely by the rate of the first step, which is the slow step. In other words, the rate which alcohol is formed should depend upon the concentration of alkyl halides alone and should be independent of the concentration of hydroxyl ion. That is, it is obvious from the expression 5.2 that the reactions follows first order kinetics. Such nucleophilic substitution reactions, which take place in two stages but in the rate determining step involves only one molecules, are known as unimolecular nucleophilic substitution reactions. Thus, the alkaline hydrolysis of tertiary butyl bromide take place through a unimolecular mechanism as depicted below. The reaction is undoubted SN1 type, as the first step involving only one mechanism is the rate determining step and the rate reaction is proportional to concentration of tertiary butyl bromide alone according to equation 5.2. The energy required to break the carbon bromine bond is a slow determining supply rate determining step is supplied by the formation of ion dipole interactions between the two kinds of ions and the solvent. Once the carbon hydrogen bond is broken, the carbocation formed rapidly combine with hydroxyl ions to yield the alcohol. From the above diagram, it may be seen that the reaction involves two transition states. Transition state first is involved in the formation of carbocations intermediate, while transition state second is involved in the combination of carbocation intermediate and OH negative ions. Since E activation for the first transition is much more than that of second transition state, it is evident that the formation of carbocation intermediate constituents the slow rate determining step of the reaction. Rearrangement of SN1 reactions. Reaction taking place by SN1 mechanism frequently give rearranged product. This is because these reactions involve carbocation intermediates which are known to rearrange to form more stable carbocations wherever possible. For example, the hydrolysis of 2-bromo-3-methyl protein through SN1 mechanism led to the formation of a rearranged product 2-methyl-2-butanol by rearrangement of the intermediate secondary carbocation or tertiary carbocation. SN2 reactions do not give rise to rearranged product as they do not involve intermediate carbocations. Let us now consider the stereochemical consequences of an S1 mechanism. The carbocation intermediate formed in the first step of an SN reaction has a flat structure since the positively charged carbon is an sp2 hybridized case. Now attachment of the attacking nucleophilic species say OH negative to the carbocation. Step 2 can occur on either face of this flat ion as shown ahead. In reactions involving optically active alkyl halides, attack of the nucleophilic species, one phase of the carbocation would naturally yield an enantiomers of the compound formed by the attack on the other phase. As such, the product obtained should be a racemic modification, the two enantiomers being expected to be formed in equal amounts. In actual practice, however, complete racemization does not take place. This is possible because of the nucleophilic substitution attacking the carbocation even before the departing halide ion has moved sufficiently away from the carbocation. In this position, the negatively charged halide ion shields the carbocation from attack on the front side, that is the same side as was the halogens. Consequently, attack on the front side which led to the product with the same configuration as the reactant is somewhat hindered by the same argument. Attack on the back side which leads to inversion of configuration is somewhat preferred. This means that the actual product would no doubt consist of a mixture of enantiomers, but the enantiomers with inverted configurations would predominate. In other words, the product form would be partially racemized. For instance, the hydrolysis of 2-bromo-octane under conditions where concentration of OH negative ions is low follow SN1 mechanism and yield a partially racemized product. Factors influencing the occurrence and rates of SN1 reactions. The main factor which influence the occurrence of SN1 reactions and their relative rates in different cases are as follows. Nature of alkyl groups in alkyl halides, electronic factors. The rate determining step of an SN1 reaction is the formation of a carbocations. Therefore, the relative reactivities of alkyl halide may be expected to be the same as the order of ease of formation and relative stabilities of carbocations. This is indeed found to be so. In keeping with the known order of relative stabilities of carbocations, the order of relative reactivities of alkyl halide is found to be tertiary halides, then secondary halides, and then primary halides, and then methyl halides. Unlike SN2 reactions, the relative reactivities of alkyl halides is S1 reactions are mainly determined by electronic factors which affect the stabilities of carbocations and not by steric factors. Nature of halogens atoms in alkyl halides, ease of eliminations of leaving group. In SN1 reactions, the formation of carbocation, which is the rate determining step of reaction, symbols easily the carbocation will be formed. As the order of ease of elimination of leaving group is iodide ion, then bromide ion, then chloride ion, then fluoride ion. The order of reactivity of alkyl halides having different halogen atom is alkyl iodide, alkyl bromide, alkyl chloride, and alkyl fluoride. It may be pointed that with respect to halogens, the order of reactivity of alkyl halide is same in both SN2 and SN1 reactions. Nature of nucleophilic reagent. Since the nucleophilic reagent is not involved in the rate determining step of SN1 reaction, it is nature does not influence the rate of reaction. Nature of solvent. Nature of solvent plays a very important role in the occurrence of SN1 reaction. This is because polarity of the solvent is crucially to the ease of formation of carbocations. Alkyl halides. In case of SN1 reaction, ionization of alkyl halide takes place only because almost the whole of energy required to reach the transition state during ionization is supplied by the formation of dipole-dipole bond between the solvent and the nonpolar transition state. It is obvious that the higher the polarity of the solvent, the stronger the solvation forces and the faster the ionization. Comparative survey of SN2 and SN1 reactions, it is clear from the foregoing discussions that while primary alkyl halides generally react by an SN1 mechanism, tertiary alkyl halides generally follows SN1 mechanism. Secondary alkyl halides can react by both mechanisms. However, it must be noted that the reactions pathway can be varied by changing the other reactions conditions as summed up below. Nature of the nucleophilic reagents. The nature of the nucleophilic reagent is an important factor in determining the actual mechanism of a reaction. Generally speaking, strongly nucleophilic reagents such as OH negative, iron negative ions favors SN2 mechanism since they can push halogens away from the molecules of alkyl halides. On the other hand, weak nucleophilic reagents such as ethyl alcohol and water tend to favor SN1 mechanism as it is easier for them to attack the carbocation already formed. Concentrated of the nucleophilic reagent. It is quite reasonable to expect that high concentration of the nucleophilic reagents would favor SN2 mechanism while low concentration would favor SN1 mechanism. This is found to be so in actual practice. Nature of the solvent. The nature of the solvent plays a very important role in determining the mechanism by which reactions occur. This is because polarity of the solvent is crucial to the ease of formation of carbocations from alkyl halide in SN1 reactions. Therefore, as already explained above, solvents of high polarity favor SN1 mechanism, while solvent of low polarity favor SN2 mechanism. Depending upon the factor listed below, the reactions may be proceeded by SN1 and SN2 mechanism. Which mechanism operates in a particular case can be ascertained on the basis of kinetic studies of the reaction. SN1 mechanism follows first order kinetics. Distinguish between SN1 and SN2. SN1 follows first order kinetics, SN2 follows second order kinetics. SN1 two-step reactions involving carbocation Intermediate SN2, single step reactions which occur through a transition state. SN1, the nucleophile can attack the carbon carrying the halogen bond on the back and front side, also the back side attack predominant. SN2, the attack takes place exclusively from the back side. SN1. In case of optically active alkyl halide, partially racemizations take place. Complete in SN2. Complete inversion of configurations take place. SN1. So reaction rate is determined mainly by electronic factors. SN2. Reaction rate is determined mainly by steric factors. SN1. Rearranged product can be formed. SN2. No rearrangement is possible. SN1. The order of reactivities of alkyl halide is tertiary, secondary, primary methyl halides. SN2. The order of reactivities of alkyl halide is methyl, primary, secondary, tertiary halides. SN1 favored by mild nucleophiles, SN2 favored by strong nucleophiles. SN1 favored by low concentration of the nucleophile, SN2 favored by high concentration of the nucleophiles. SN1 favored by solvents of high polarity, SN2 favored by solvent of low polarity. Eliminations reactions E2 and E1 mechanism. While discussing the mechanism of dehydrohalogenation, a typical eliminations reactions of alkyl halide, it was stated that the reactions take place by a single step biomolecular reaction. It is alkyl halides. It was stated that the reactions take place by a single step biomolecular process. It should be, however, noted that this is not the only possible mechanism of elimination reactions of alkyl halides. Like the nucleophilic substitutions reactions, the elimination reactions of alkyl halides may also two different mechanisms. These two mechanisms called E2 and E1 mechanisms. E2 mechanism. The mechanism involves a single step biomolecular elimination. It is assumed that the attacking base involves a proton from a beta carbon with the simultaneously loss of alide from the alpha carbon and the formation of an additional the two carbon as depicted below. The reactions follow second order kinetic and the rate reactions depends upon the concentration of both hydroxyls and alkyl halides. Structural factors influence the and on E2 reactions have been carefully investigated for a given alkyl groups. The rate of eliminations varies with the nature of X in order Ri, Rbr, Rcl, Rf for a given X. The ease of eliminations follows the order tertiary halides, secondary halides, primary halides. Unlike SN2 reactions, E2 reactions are not appreciably influenced by steric factors and take place easily with tertiary halides. The E2 reactions, however, generally brought about by rather strong bases. In case of alkyl halides having unsymmetrical R group like tertiary amyl chloride, it is possible to have two different alkenes formed depending to have two different alkenes. E1 mechanisms. The mechanism operates through two-step process in which the rate determining step involves only one mechanism. It is believed that in the first step, which is the rate determining step, the alkyl halides dissociate into halide ions and carbocations as in SN1 reactions. The carbocation loses a proton to the base and forms the alkane. It is obvious that the reaction follows first order kinetic as the rate determining step involves only one molecule. The rate of the reaction is independent of the concentration of base and varies only with the concentration of alkyl halides. Many secondary and tertiary alkyl halides undergoes E1 type of elimination in solutions. Base concentration, structural factors, influences of E1 reactions are similarly to those of SN1 reactions for a given alkyl group. The order of reactivities of two different alkyl halides is Ri, Rbr, Rcl, Rf. For the same halogens, the ease of elimination is in the order tertiary halides, secondary halides, primary halides. It should be noted that unlike SN2, SN1 reactions, the order of reactivities of alkyl halides in both E2 and V1 reactions is the same. Like E2 eliminations, even elimination also tend to favor the formation of more stable or highly substituted alkene. In case of alkyl halides, where eliminations can take place in more than one direction, for example, like SN1 reactions, even eliminations reaction may also give rise to arrangement products due to the rearrangements of carbocations. It has been already stated that alkyl halides can undergo both substitution and elimination reactions. Moreover, the reagents which bring about the two types of reactions, that is nucleophilic reagents and the bases, are essentially similar to each other. All nucleophilic reagents are basic and all bases are nucleophiles. In other words, the same reagents can bring about both elimination and substitution reactions of alkyl halide. As a substituent and elimination reactions of alkyl halide usually proceed simultaneously in competitions with each other. For example, in the reactions of ethyl chloride with sodium hydroxides, eliminations to give ethylene competes with substitutions to give ethyl alcohol. It is therefore important that in synthetic work we should be able to have as much control as possible over the relative proportions of the possible products. This can be done in the light of various factors which influence the occurrence and ratio of two types of reactions. These factors have already been discussed in detail earlier. However, a brief description of their roles in substitutions versus elimination is given below. Biomolecular substitutions and eliminations reactions. The transition state formed in these two types of reactions are different from each other. Therefore, it is possible to influence the ratio of substitution and eliminations product by varying the structural and solvation factors. Nature of alkyl group. For alkyl halides containing the same halogen atoms, the order of reactivity in SN2 reactions is primary halides, secondary halides, and then tertiary halides subsequent. On the other hand, in E2 reactions, the order of reactivity is just the opposite, that is, tertiary halide, secondary halide, and one halide subsequent. Thus, the E2 reaction is increasingly favored as we change from a primary to a secondary to a tertiary alkyl halides. Even for alkyl halides belonging to the same class and containing the same halogens, the size of the alkyl groups and branching at beta carbon atom influence the relative rates of SN2 reactions and E2 reactions due to steric hindrance. With the increase in the size of alkyl group and or increased branches at beta carbon atom, steric hindrance increases and this in turn slows down the SN2 reactions. As a result, the proportions of elimination product increases. For example, in the reaction with sodium ethoxide CH3CH2Br undergoes 99% substitution and 1% eliminations. For example, CH3, CH2, CH2Br, the relative proportions are 91% and 9% to 99%, while CH3 twice CH, CH2Br substitutions take place to the extent of only 14% and eliminations reaches 60%. This is in spite of the fact that all alkyl halides considered above are primary alkyl halides. Nature of halogen atoms. For the same alkyl group, the nature of halogen atoms does not significantly alters the substitution eliminations ratio. Nature of attacking reagents. Natures of attacking reagents. SN2 reactions are favored by strong nucleophiles while E2 reactions are favored by strong bases. In general, strong nucleophiles are strong bases as well. Therefore, elimination reactions compete strongly with subsequent on reactions. However, the reagent used is a strong nucleophile but a weak base. Substitution is favored over eliminations. Nature of solvent. Both SN2 and E2 reactions are favored by solvents of low polarity. However, decreasing polarity elimination is favored to a greater extent. Effect of temperature. Higher temperatures favor E2 over SN2 reactions. Unimolecular substitutions and eliminations reaction. As already studied, the first step in both these reactions is the heterolytic cleavage of the carbon halogen bond of alkyl halides to form the carbocation. It is the second step that the two reactions follows different paths in the substitution reaction. The attacking reagents attach the carbons to bring about nucleophilic substitutions, while the eliminations the attack takes place at hydrogens to build the alkene. It is therefore obvious that the substitution elimination ratios will depend upon the relative rates of the second step in the two cases. If the substitution reactions, the least stable carbocation would be attacked more readily to the substitution process, since the increasing order stabilities of carbocation is one primary सबसे कम, then secondary and then ना primary सबसे कम, फिर थोड़ा ज़्यादा secondary and फिर सबसे ज़्यादा tertiary. The rate of substitution is should follow the sequence primary सबसे ज़्यादा, then secondary, then tertiary सबसे कम. In elimination, the ease of loss of proton by the attack of hydrogen is determined by the stability of the alkene formed. In keeping with the order of stabilities of the alkenes, the rate of elimination from the carbocation follows 3 greater than 2 greater than 1. Sum up, it may be stated that as we change from primary to secondary to tertiary alkyl halides, the proportion of elimination product goes on increasing. Effect of temperatures. The other reactions variables in unimolecular reaction is temperature. Generally speaking, higher temperature favor even reactions over SN1 reaction. It is interesting to note that in biomolecular as well as unimolecular reactions, probability of elimination reactions on moving from 1 to 2 to 3 alkyl halides on carrying the reaction at higher temperatures. Relative reactivity of allyl halides with respect to alkyl halides. Allyl halides are monohalogen derivative of alkenes in which the halogen atom is attached to the carbon atom alpha to the carbon-carbon double bond. They are found to be even more reactive than alkyl halides in nucleophilic substitution reactions. They can undergo both SN1 and SN2 reactions. To understand this, let us recall the reactivity. S1 reaction is mainly determined by electronic factors, while the reactivity in SN2 reactions is mainly governed by steric factors. The allyl groups present in allyl halides represent a remarkable species. On the other hand, it can give rise to a carbocation stabilized by dispersal of positively charged due to resonance. Alkyl halides are resonance stabilized allyl carbocation. The stability of allyl carbocation is comparable to the stabilities of the secondary and tertiary carbocation, which undergoes dispersal of positively charged due to inductive effect. On the other hand, size of the allyl group is just above as much as that of iron-based primary alkyl groups. In other words, alkyl halides are sterically similar to primary alkyl halides and do not hinder the approach of a nucleophiles. Reactivity in SN1 reaction due to the resonance stabilizations involving the dispersal of positively charged allyl carbocation can be easily formed from allyl halides. The net results in that like secondary and tertiary alkyl halides undergoes SN1 reactions steadily. In fact, allyl halides undergo SN1 reactions at about the same rate as the secondary halides or even faster than that too. Reactivity of SN2 reactions since primary alkyl halides does not offer steric hindrance to the approach of attacking nucleophiles. It undergoes SN2 reactions with the same or even greater readiness than primary alkyl halides. Relative reactivities of vinyl halides with respect to alkyl halides. Vinyl halides are monohalogen derivative of alkenes in which the halogen atom is attached to carbon carrying the double bond. The chemical behavior of vinyl halides is marked by lack of reactivity towards the nucleophilic substitution reactions. This behavior is in sharp contrast to that of alkyl halides. Let us now try to see as to why the halogen is vinyl halide is so inert towards nucleophilic substitution. Explanations based upon resonance. A vinyl halide is a resonance hybrid of two structures as depicted below. In case of vinyl fluoride, as a result, the carbon-halogen bond acquires a partially double bond character due to the contributions from structure such as 2. Thus, in contrast of alkyl halides, vinyl halides exist in the form of resonance stabilized molecules in which the halogens is firmly attached to the carbon. As such, the halogen in vinyl halides cannot be easily displaced by nucleophilic reagents. The above interpretations of the low reactivity of vinyl halide is also supported by their dipole moment values. For instance, vinyl fluoride has a dipole moment of only 1.4 d, while the dipole moment of alkyl chlorides are of the order 2 to 2.2. This means that the vinyl halides are much less polar than alkyl halides. This is obviously due to the fact that the contributing structures such as tends to oppose the development of negatively charge on the halogen arising from the displacement of electrons of carbon halogen bond towards the more electronegative halogen atom. Even though there is still a net displacement of electrons towards halogens in vinyl halides, it is less than in alkyl halides. This naturally inhibits the displacement of the halogens. Alternative explanations. There is another explanation also for the low reactivity of vinyl halides. The carbons carrying the halogens in vinyl halide is sp2 hybridized, while that in alkyl halide is sp3 hybridized due to the lesser reactive size of sp2 hybridized carbon as compared to sp3 hybridized carbon. The carbon halogen bond of vinyl halide is shorter and stronger, and the molecule is more stable. An idea of the bond length of carbon halogen bond in vinyl and alkyl halide may be had from the fact that the carbon chloride bond length in vinyl chloride is 1.69 angstrom, while in alkyl chloride the length is about 1.80 angstrom. This interpretation is also in line with the less polar character of vinyl halides. It may be recalled that the sp2 hybrid carbon atom is more electronegative than sp3 hybrid carbon atom. As such, the sp2 hybrid carbon halogen bond in vinyl halide is less willing to release the electrons to the halogen, and consequently this bond is less polar. Thus, the low reactivity of vinyl halides toward nucleophilic substitution reactions can be attributed to two reasons: classification of electrons by resonance and attachment of halogen to sp2 hybridized carbons. Thank you.